All right. So we will start today's lecture. This is what we were discussing last time, which is that what are the quantities, what are the physical properties of crystalline materials that we will eventually discuss that we can uh, predict by trained machine learning models. And I discussed some properties, and the main message at the end of it all that I wanted to convey in the last lecture is that you have to be careful about what is the meaning of the quantity that uh, you are that is your target. So as an example, I talked about band gaps. Band gaps are often calculated. There are sets of measurements through which band gap is measured, but then there are different band gaps. Although they are all called gaps, but physically they mean different things. And if you measure two different types of gaps in the same material, you will get different numbers. So, therefore, when you are preparing your training data to train a machine learning model, you have to be consistently using the same quantity, just to be sure. Usually it doesn't become a problem if your source is a single data set which has been prepared using a single method or a single type of measurement. But if you're trying to mix two different data sets just to increase your training set size, then you have to be extra vigilant that they are consistent. So it's not just about different measurements. If band gaps are calculated at different levels of theory, then of course you get different results, different numbers for the same material. So you should not mix these quantities, and this applies to all physical quantities, all physical properties, not just band gaps. Okay, and then we came to this point that in order to train any model, you need data. So, where is the data? Where can you find materials data? Today, we'll get familiar with some of the extensive material data sets that are available. So, one of the oldest and most extensive experimental data set, that is data set for materials that have been experimentally synthesized, verified, is the inorganic crystal structure database, or ICSD. As I told you last time, uh, is it uh, yeah, I hope the ICSD webpage is visible on your screen. If not, just write in the chat box, or someone please let me know. So some of you may be familiar with it, you already use it, others you get familiar with it. Only thing is that this is not free. So it's the world's largest database for completely identified inorganic materials. Uh, All structures are verified, but it is not free. You need a subscription to access these database. So that's the first database I wanted to show you. Then the next one is crystallography open database. It's again one of the many experimental databases, and this, as the name suggests, is an open database. So here is the website for this database. You can browse what are the materials. So it basically arranges information according to the year of publication or the journals in which the original papers have been published. You can search materials in this. If you are it's not possible for me to go through all the details, all the options that you have here. But just to show you, for example, I want, let's say, binary and ternary material. So the number of distinct elements in the material can be minimum of two and maximum of three. And I specify some materials, some elements. So let's say iron and oxygen. So, and then I just type send, and it will show me all the materials available that contain iron and oxygen. It may contain, these may contain other elements also, like here in this case is silicon, in this case vanadium, and so on. But there are ways you can just restrict it to only oxygen and iron. So you can explore this and see what are the materials that are available. So if you click on this, you get information about the crystal structure in what is called CIF format, crystallographic information format, or file, whatever. This is an internal ID that they use, and this is the last column is the original paper in which this experiment was published. So it's one of the very useful databases for experimentally verified structures. You can also download the entire crystallographic open database archive as a single zip or tart zip files if you are interested. Okay, so these are the two experimental databases that I wanted to make you familiar with. Now, as it turned out, in the last lecture, I talked about the Materials Genome Initiative, and this Material Genome Initiative has actually spawned a number of efforts throughout the world which have come up with DFT generated databases. We discussed the general problem that experiments are always difficult, expensive, time consuming. The next best thing you can do is quantum calculations, and density functional theory is the way to go. So, large scale density functional calculations have been done, and large databases have been generated. Some are experimentally known, synthesized, studied materials. There are a large number which are just theoretical materials. Nobody has yet synthesized those materials, but they have been calculated and they turn out to be extremely valuable in our application of machine learning to materials science, as we will see and understand as we go along. So in the next slide, I list a few of these databases, and eventually we will work with three. I'll show you in detail how to access data, materials data from three of those databases, and then how to construct your data set, training data set for model training, and how to use those for training model. So those will be the sort of hands-on sessions. So number of these are listed, and these are all freely available DFT databases started after the launch of MGI, Materials Genome Initiative. Now, anytime if you are using it for your course, for your private practice, your project, doesn't matter, but anytime you want to use any of these databases for publications, particularly if you use it for any commercial purposes, of course you have to be very clear about what are the license agreements, what can you do and not do with it. And that's not something I will get into it, but you can get on the respective websites. So first of all, let us get familiar with the MGI website. It's a very it's something you should often come back to make an to sort of build an understanding of where the materials research is headed. So this is the main web page of the Materials Genome Initiative, and these are some of the present highlights. So you see, so one of the focus areas is new dielectric polymers for wound film capacitors. Here is another one, seeking materials with high melting temperature and structural stability. So they are looking for materials that have large elastic constant, mechanical strength, and also high melting points. The other thing I wanted to point out here is this thing. autonomous experimentation for materials R&D, something I mentioned in my very first lecture and perhaps in my previous lecture as well. I don't recall, but there is a working group, and they met recently, or maybe June last year, and there's a report of that meeting that you can access in this link. So this autonomous experimentation is something like you have an autonomous agent. It's like another researcher in your lab, except that it's not a human researcher, but it's AI driven researcher. Given a target, this autonomous agent can, of course, you have to start it with some previously known knowledge data. Once you give that data, that knowledge to the agent and give a target, it can on the go, it can learn from its experience, make decisions, and gear the experiments towards that goal. So you may want to get into, get a feel and understanding of what this really means and where it is headed. Okay, so that's the main sort of parent materials genome initiative. Then one of the big resources, perhaps the biggest one for getting DFT generated materials data, is the materials project. So here is the main materials project website. Take a minute or so to load. Yeah. So as you see, as of now, there are 200,000 materials, inorganic materials, that are available on this site. Then there are 577,000 molecules, structure, and other information that are available. And here, one thing I will show you right now. How to get data from here, I will show you later. Phase diagram. Okay. So we talked about this convex hull and hull diagram and so on. Let us see if we can understand that a bit better. So suppose I choose these two elements, iron and oxygen, and I ask it to generate the phase diagram. Yeah, so here you see you have the convex hull diagram for the iron oxygen phase space. Here is the fraction of oxygen along the x-axis. So on the left you have pure iron. So here you see you have pure iron. This is the iron in its ground state structure. I believe iron is BCC. And then as you start moving along this direction to the right, more and more oxygen. So the fraction of oxygen increases, and by the time you reach here, this is oxygen. And O2, that is the reference state for oxygen in all these calculations. All these formation energies have been calculated by considering the reference state of oxygen to be O2 gaseous molecule. So isolated O2 molecule, whereas iron, it's not given here, but I believe it's the BCC form of iron. And each one of these points, so the green points are the materials which are on the hull. So they are obviously stable materials. And the ones that are above the hull are not, they are higher in energy. So even at a given composition, for example, FeO here, there are many FeO. So they must differ in structures, crystal structure, and therefore they have different energies. And as you go vertically up, you get higher and higher energy polymorphs of FeO. If you come here, this is oxygen in other forms. And here, for example, you have Fe4O13. Here you have another Fe4O13, and so on. So that's a binary phase space. Let us see if we can understand a ternary phase space. So what I put in was iron, nickel, and oxygen. So that is the triangle I talked about last time. This corner is pure iron, this corner is nickel, and this corner is oxygen. And then as you move inside, you have you know the ternary phases. So let us pick one of these. So this one is FeNiO3, and here you have Fe7Ni3O82, etc., etc. And this green one, so the green ones are the ones which are on the hull. They are the most stable known phases. And if you move along one of these sides, you are in a binary phase. So this line is iron nickel binary phase. This one is nickel oxide binary phase, and this is iron oxide binary phase, which we just saw. Okay, so now you have some idea of what these hull diagrams actually look like. We'll see one more where you can put in your own material. Okay, so I'll show you an example of that. Just give me a minute. Yeah. So the next one we look at is OQMD, Open Quantum Materials Database. I'm showing you these things, spending a few minutes on each one of these, because I want you to sort of practice with this, because when you do the projects, you will find this useful. So this is the Open Quantum Materials Database, and we are interested in the phase diagram. So you write, click on create, and let's say I am interested in the MnNi oxygen phase space. Okay, it is taking a while. Usually it doesn't take so long. Ah, there you have it. MnNi oxygen phase space, again a ternary phase diagram. The green circles are the ones are the materials on the hull. The red ones are above the hull. Now, what I wanted to show you here is that suppose you have theoretically calculated the formation energy of a compound, and it's irrespective of whether it's experimentally synthesized or not, you don't know where it is on the hull, how far it is above the hull, and so on. So how do you find that out? You can use this web page, use this site to actually figure that out. So another aspect of this that I wanted to show you is that right now it is showing materials, all the materials that are up to 0.25 ev per atom above the hull. If anything is farther away from the hull, that is not plotted in this diagram. Okay, uh, to reduce the number of materials, make it a little less crowded, or if you are interested only in a smaller energy region above the hull, you can change this number. So let's say we make it 0.1. And experimentally, any material that is within zero point 0.1 ev per atom of the hull is generally considered to be easily synthesizable. So we hide phases that are more than 1 ev per atom above the hull. See, some of the materials have been removed, they are not ticked anymore. So you have a so I have to make it once again. So I reevaluate the hull with this button, and I go back, and you have a less crowded phase diagram. There are fewer materials now. Now I have a new material that I have calculated. and I want to put it on this and see where it is with respect to the hull. How do I do it? I go to the bottom, and you see this button, add a row. So I click on that, and the material I have calculated, excuse me, MnNiO3, and I have to give its formation energy in the same units, EV per atom, and the number I have is minus 1.638, and I reevaluate. Where is it? MnNiA3. This is where I have it. This is my material, which was earlier not present. Now it comes into the picture, and you see it has a formation energy minus 1.638 ev per atom. And I can check. So this column stability means where it is relative to the hull. So I go here again. So it turns out to be on the hull. So it is a particularly stable material, and it should be. So that's how you can use this OQMD, phase diagram module. Of course, there are materials here that you can download for your model training. All right, so that's about Open Quantum Materials Database. Then Aflow is another very well-known, very popular data repository, as well as a suite of softwares that allows you to do high throughput computation, but I will not discuss that. We will spend some time getting familiar with the next one, which is computational materials repository. So let's open this. Yeah, this is computational materials repository, and again we will spend some time understanding how materials data is organized on this site, how you access it, and then how you extract data, create your own data sets, etc. Today we'll quickly go through to have an overview of what kind of materials data are available on this site. um, some of the important ones. I'll not talk about everything. So this one, for example, chemisoption of gas atoms on one-dimensional transition metal halides. Okay, so adsorption energy of some gas atoms on one-dimensional transition metal halides. This is some database which gives you impurity energies in 2D materials. This is a database of materials of the form ABAC3. So AB can be whatever. Then triselenide materials. So this is something we will spend some time on. Then there is a similar ABS3 materials database you see here. Okay, sulfides and selenides. Screening for photovoltaics and PEC materials using OQMD database. That's okay. Here is a database for organometallic halide perovskites, etc., etc. And one thing you should keep in mind that these databases evolve. They keep evolving. New data are added to these data. Most of these databases periodically. So what you see today, things might have changed significantly a year from now. So therefore you should keep coming back to these databases. So there are all these databases that you find in this on this site. And so download data is something we will do later. So we are now looking at the ABAC3 database. You can browse data. If you go there, it will list all the 5,976 materials that are there in this database. So here is the prototype. Here is the actual system, stoichiometry of the system, space group, total energy, heat of formation, the same as formation energy, and yeah. So you can add more quantities. For example, just for the sake of it, I I add unit cell volume. So this gives you unit cell volume, just in case you want to use it for as one of your features in some model training, or just want to have that information. Okay, so that is about computational materials repository. We'll look at it in more detail later on. Novomag and Novamag are two databases that specifically contain magnetic materials. Now, I will not discuss these things in detail or show you how to extract data from these. But if you are interested, you go to these sites and figure it out yourself. Okay, Alexandria is something I will show, although we may not use it in the exercises in this course, but I will show you how to download data from Alexandria and yeah, and how you can sort of create your database. Finally, yeah, so Alexandria, let me show you quickly. Yeah, this is the Alexandria database. You can click here. It's taking a while. So we'll come back to this when we actually show hands-on how to download data. But let's see if we can get to the Jarvis data set. Yeah, this is Jarvis, maintained by Jarvis is an acronym for Joint Automated Repository for Various Integrated Simulations. It is maintained by NIST, the US government research organization. And if you want to see what data are available, click on databases. Here are the databases. And so here is the link. And on the right, you have description of that database, each database. So for example, the first one is DFT calculation for 80,000 plus materials, millions of properties using OPT-B88 VDW and TBMBJ methods. These are specific methods, approximations within density functional theory. There are calculations including spin orbit coupling, without spin orbit coupling, for those of you who know what this means. But again, the point is you cannot, should not mix materials data calculated with spin orbit coupling with those calculated without spin orbit coupling. That won't be correct. Okay, so these are some of the major DFT generated data. All these are DFT generated databases. I showed you the basic, web pages of some of these. How to access data, we will discuss later on. Some are very straightforward, some are require a bit more work. Okay, so downloading data is something we will get to later. But now that you have some idea of where to get your materials data, you can be more confident about, proposing your projects. So you know that materials data are available. You can do a search, see what kind of data are available, and possibly what kind of models you would train. All right. Are there any questions at this stage? No, I don't see. All right. Just give me a minute. Fine. So we know where to get our materials data. And then comes the big question that how do I train my models? You are already familiar with different kinds of machine learning model, linear regressor, etc., whatever, tree-based models, the random forest, the KNN, etc., the SVM. You are familiar with all of those. But what you need in order to train any model, to predict materials property or materials features. So what are material features? So let's see what we do. What do we do in our theory-based paradigm, theory-driven research approach? If we are interested in calculating properties of a material, crystalline material, the first thing we have to understand is its crystal structure. So, for example, if you are interested in an FCC material, you already know from your basic solid state physics course that if A is the cubic lattice constant, then these are the primitive lattice constants of an FCC lattice, and you just have to specify one atom. So it's a one atom basis at the origin. These are your lattice vectors, and then you have defined your crystal. But then not every solid material can be described with one atom in the basis. For example, if you take the zinc blend structure, and this is something I will show you in a minute. It's an FCC based structure, but it's not one atom in the unit cell. If you describe it in terms of these primitive lattice vectors, you need two atoms in the unit cell. If you describe it in terms of the conventional cubic cell, then you need eight atoms in the cube to completely describe this crystal. So things can be complicated sometimes. So zinc blende structure is FCC with two atoms at the unit, two atoms in the unit cell. So one, let's say sulfur at 0, 0, 0, and then zinc will be at 1/4, 1/4, 1/4 in units of A. All right. So let me see if we can understand this zinc blend structure, and then it will help us understand the subsequent discussions. Well, here is the zinc blend structure. I will not sort of describe it in great detail. You can open any solid state book and you should find it. But the way it has been described on the slide is that you have to specify, this is a cubic cell, of course, the conventional cubic cell. But in terms of primitive cell, you need these two atoms, the sulfur atom at 0, 0, 0, and the zinc atom at 1/4, 1/4, 1/4, and then you can describe the entire lattice. Or if you describe it in terms of the cubic cell, then you need to specify eight atoms within these, within this cube. All right. So what am I trying to say here? What I'm trying to say here is that this is how we learn about crystalline solids, and this is how we like to, this is the human intelligible way of representing a material. But is this the best way of representing a material for a model? What are the problems with this for a model? What if the material is rotated? So this is in terms of some, say, fixed set of axes in space. If I rotate, so I have a piece of material, if you can see me, here is my phone, assume that it's a piece of material, and I rotate it in some arbitrary way. So it was like this, then I rotated it like this, then I rotated it like that. So in any arbitrary orientation in space, when I rotate it with respect to the set of fixed axes in space, these things will change. Okay, these numbers will change, but the properties of the material cannot change. So if we represent a material this way, that property of rotational invariance of the property of, say, the formation energy is not captured. Then I decided to put the sulfur atom at the origin and zinc atom at 1/4, 1/4, 1/4. I could do it the other way. I can put this zinc atom, I can call this, I can shift my origin here. This is now my origin. And at 1/4, 1/4, 1/4, I put a sulfur atom. That is also an equally valid description of the material. So if I translate my unit cell, uh, nothing changes. The properties don't change. So that is again not captured in this human intelligent way of representing a material. Thirdly, and if it is easiest to understand in terms of molecules, if I translate a molecule is here, and I translate it uh, rigidly to some other point in space, its property cannot change. If I represent a molecule in terms of the xyz coordinates of the atoms, then of course that will not capture this translational invariance. Also, property of any material depends on the chemical properties of the constituent atoms, and just specifying the atoms may not be enough, because this way, we know what kind of an element zinc is, we know what kind of an element sulfur is from our knowledge of chemistry, but the model doesn't know unless you tell it. So therefore, quantities like the ionization potential, electron affinity, electronegativity, etc., of the constituents should be. And from our knowledge of chemistry, we know that these are important in determining the properties of a material. But this way of specifying, will not tell the model what these are. So these are some of the limitations that a human intelligible way of representing a material is not the best way for a model. So what are the requirements finally? What are the requirements of the features for model training? So this is now a sort of elaborate discussion. Let me sort of tell you right in the beginning. So I'll go point by point, and this is somewhat formal, parts of it at least, not always intuitive. But once we understand it, we understand materials features better. Okay, now I have to go to the smart. So what are the requirements of an ideal feature? First, the feature should contain all information that are required for determination of the property of interest. Let me give you an example. Graphite and diamond are both made of carbon atoms, but their crystal structures are different. And it is this difference in crystal structure that makes all the difference in properties of graphite and carbon. And they are very different properties. So, therefore, it's kind of obvious that structure is important. If you do not give the structural information, specify only the constituent atoms or their chemical properties, you have not given complete information about your material. That is the first point. It has to become, this is just an example, but you can possibly cook up other examples like this. So it has to be complete. Okay. Now, a priori, it's very difficult to say what is complete and what is not complete. Uh, but let's see if we can develop some understanding as we go along in the course. The second point of non-degeneracy is a bit formal, but let me try to slowly go through it. Those of you who are, or you may have, all of you may have seen these kind of Hamiltonians during your, for example, atomic physics course, even if you have not done electronic structure or many body physics course. So this is the electronic Hamiltonian for electrons in any molecule, material, whatever you have. So the first term is the kinetic energy operator for this is a quantum mechanical Hamiltonian. The first term is the kinetic energy operator of the electrons. The second term is the interaction energy between electrons whose positions are small ri's, and the nuclei whose positions are capital Ri. And the last term is the electron-electron interaction energy. Now, why am I invoking this quantum Hamiltonian? Now, suppose, because after all, all properties of materials are determined by the principles of quantum mechanics. So, let us see. If we have two materials, M1 and M2, and when I say two materials, two distinct materials, these are not rotated or translated copies of the same material. These are two materials, distinct materials, differing either in structure or in composition or both. And the demand is that they should produce different feature vectors x1 and x2. Uh, if m1 and m2 both give you the same feature vector x, they will be predicted to have the same property, right? If your model predicts properties based on the feature vector, if m1 m2 lead to the same feature, then their properties will be predicted to be the same. But that is in general not true. No two distinct materials have any property that are exactly equal, unless, except for some very special cases. So more formally, how do we argue for it? How do we understand it? If M1 and M2 are different materials, the quantum Hamiltonian describing the electrons in these materials have to be different, some one way or the other. If the Hamiltonians are different, then the ground state wave functions of the electrons in these materials have to be different. So psi1 is not equal to psi2. Now, quantum mechanically, how do we calculate value of some property? It's the expectation value of some observable O that represents that physical quantity. So because psi1 is not equal to psi2, the expectation value of the observable O, the operator O, in the state psi1 is not equal to that in state psi2. But the quantum mechanics then tells me that they are not equal yet. If m1, m2 lead to the same feature vector, my model will give me the same number for numbers for both the materials. So that is obviously wrong. That contradicts quantum mechanics. So it should not be. It cannot be. So therefore, it's a strong argument that you should have non-degeneracy in feature vectors. Is that always satisfied? Depends on what you have available at hand. Now we will get to that discussion in a while. Compactness: features should contain minimal amount of information relevant to the target property. Having more information will make training process complicated. This is unnecessary. Again, these are all, these statements are made formally very easily, but actually ensuring implementing all of that in practice is not always easy, not always positive, but it's good to know these formal aspects. So how do we understand this? So suppose we have a molecular solid made up of some molecules which are chiral. Now, chiral molecules are, you can have two kinds of structures of the same molecule, but they cannot be put on top of each other. They are mirror images of each other. That's one easy way of visualizing it. And what differs between these objects is that their optical properties are different. One will rotate a polarized light, the other will not. So therefore, if we are interested in describing optical properties of a material, then of course we have to have chirality in my feature space, because otherwise it is not complete. It cannot describe optical properties. On the other hand, if we are not interested in optical properties, say I'm only interested in calculating or predicting energies, then that chirality doesn't matter. They are energetically the same. Therefore, having information about chirality could be overdoing it. It's unnecessary information, and we may easily, or we better, omit it. Okay, I hope that explains the concepts of completeness and compactness. Uniqueness, it's a one-word description for rotational, translational, permutational invariance. I didn't talk about permutation invariance, but suppose I have a material composed of, say, 5 atoms in the unit cell. And in whichever way I specify these atoms, it should not matter which one is put first and which one is last and in which order they are put. As long as their positions are the same, the structure is the same, I should get the same answer. So rotational translation and invariance I have already talked about. So it basically means, because the properties do not change under these transformations, my feature vector, my features should also be invariant. If the features are invariant, then the predicted properties are also invariant under rotation, translation, or permutation. Meaningful. The feature vector that you use should be meaningful in the context of the complexity of the model. Now, I have mentioned several words, several terms. Let me try to slowly explain. So what we are trying to do is, I have a trained model which maps features to some physical property. This relation should be such that, given the features that I'm using, this property can be described. Let us take an example. If a particular property depends on the square of some feature x, and we are using a linear model, it cannot be meaningful, right? A linear model can never capture a relation which is quadratic in x, if I'm using x as a feature, obviously. However, in the same linear model, if I'm using x squared as a feature, then obviously it will be able to capture the fact that the property is determined by or depends on x squared rather than x. You can make things more complicated. It need not be x squared, it could be some other complicated form depending on x, general non-linearity. And in all practical situations, we talk of feature spaces that are many dimensional. There are many features or components of the same feature, and there can be complex interplay between them. So therefore there can be all sorts of non-linearity, and your features should be such that within the complexity of your model, uh, it should be able to describe the relation from feature to property. Complexity of a model in general depends on model type, number of parameters, number of hyperparameters, and so on. And the general, I think we will discuss it, and it will be up to you know, Dr. Mishra to discuss it. That when we do neural networks, in principle, we are able to capture any kind of non-linearity between the features and property, or any features and the target quantity. Some material specific things again. Continuous features should change continuously with change in composition. Our chemical intuition tells us that if we change the composition of a material slightly, the properties should also change only by a small amount. So suppose you had an alloy which was equal FeCO, and you change it by tiny amount. You increase cobalt concentration by 0.1%, decrease iron concentration by the same amount, and the property cannot be hugely different. So therefore, because the property changed by a small amount, you better construct features that also change by small amount. So the features should be continuous with respect to change in composition. Features should be differentiable. Small changing in positions of atoms are expected to change the property of a material. A similar argument by a small amount. And so this property should change continuously with respect to movement of atoms. And because the property is a function of features, you better have features that also change continuously and are differentiable. So these are again very formal statements, but just to be aware of these, that there are these discussions in the literature. A more practical thing is features should be uncorrelated. This is true of any machine learning exercise, not just about materials. If two or more features are strongly correlated, keeping both of them is not really helpful, because you are not adding any independent information. Sometimes it can even complicate model training and reduce its performance. So we can keep one of those, or there are more systematic ways of removing some of the correlated features, and possibly we will discuss at least one of those uh, subsequently. And a very, very practical statement at the end is that construction of features should be easy. Computationally, it should be easy to construct features, because if constructing features take more time than making predictions, then it's not very useful. So they should be computationally easy to construct. Okay, so these are some of the requirements of ideal feature vectors. When I create the PDF, I have to do something about this figure. All right. Having gone through that discussion, let me see if there are any questions at this stage. I don't see. Okay. Now, having gone through these formal discussions, let us now discuss some of the features that have been developed, used in the literature to uh, predict materials properties, for materials classification, etc. And you will see that many of the features do not satisfy. I don't think any of the features satisfy all the properties, and many of the features do not satisfy some of the most important properties, or what intuitively would look like the most important properties. So we'll start with the simplest features that have been used, and then increasingly go to more complex things. Okay, so what is the basic information that you need about a material? When you are predicting properties, calculating properties, what you need is information about structure and composition. What are the atoms forming the material, and where are these atoms located? Turns out that some of the features that were constructed and used, but they were not used in isolation, they were mixed with other features that we will get to, uh, carried information only about the stoichiometry, that is the composition of the material. So let us look at this. So for the first thing that was used was called the stoichiometry norm. Now, what is the stoichiometry norm? You have a material consisting of several types of atoms, and xi is the fraction of number fraction of some particular atom. So you construct this quantity. This is called stoichiometry norm for a particular p. P can be, one is of course trivial. It will add up to, for p equal to 1, you always get 1, but it could be 2, it could be 3, and so on. And this quantity, or these quantities, are called stoichiometry norm. So let us take an example to understand this. If I take Fe3O4, the well-known material, then the atomic fraction of iron is 3/7, that of oxygen is 4/7, and therefore the stoichiometry norm for p equal to 2, you can easily calculate this. This number turns out to be 0.071. For order 3, it's 0.064, and so on. And I haven't seen uh, anyone going beyond this. Then you can calculate the second quantity, is called stoichiometry entropy. So again, xi's are the atomic fractions. There should be a negative sign here. Yeah. So again, with the example of Fe3O4, AC turns out to be 0.68. And as you see, these are, I mean, we argued at length that features should not be unique, but these particular features will be unique and will not be unique anytime you have a material with a composition A3B4. Okay. But as I said, these were not used in isolation. So if you use only stoichiometry as your feature to predict properties, you really can't do anything. Okay? Any material which is of the form A3B4 will have the same value of the stoichiometry entropy. So in that some sense, that is useless. Atomic vector is another quantity that was used. So it's a vector of length z max, where z max is the maximum value of the atomic number among all the materials all the elements that you have constituting the materials in your database, training data. So in your training data, you have a large number of materials. Each one is consisting of certain number of elements. And you look at all these elements in the entire data set. What is the Z max? You ask the question. So that is the length of this vector. And what is the vector for a given material? The first position is for hydrogen, the second one is for helium, third one for lithium. As you go in the periodic table, this is the most sensible way of doing it. And corresponding to that site, you just put the atomic fraction. So, for example, for VO2, in place of oxygen, oxygen is what? Oxygen is 8. So you put 2/3. In place of vanadium, you put 1/3, and that's it. The rest of the elements are 0. This has been used, at least in one of the papers. Okay. Then, so these features, the features in the previous slide, these contained information only about the stoichiometry of the material. The next set of features that were constructed contained information about both stoichiometry and chemical properties. So some chemical property of the constituent elements were also built in, as we argued that quantities like ionization potential, electron affinity, electronegativity, etc., are useful in determining materials properties. So here Q is any atomic property. Now, what atomic properties are used are listed here. Some works use a longer list of properties. So first of all, one quantity you can define easily is the configuration weighted average. So again, xi's are the atomic fractions. Qi is the corresponding quantity for the ith atom, and you construct a configuration weighted average. Configuration, then the next quantity is configuration weighted absolute deviation. So it's deviation of the property for the ith atom from the average, but weighted by the configuration, weighted by the atomic fraction xi. So again, you have this quantity. Then the third quantity that was used is on configuration weighted mode of the quantity q. Normally, Q is defined as the mode you do in statistics. So it's the maximum value of Q among all the elements in a material. If two elements happen to have the same value of Q, two or more, then you take a simple average of those. And as I said, some of the elemental quantities that have been used are atomic number Z, the period number P, the group number G. This is the period on the periodic table to which the element belongs. Group number G, the group in the periodic table to which a particular element belongs. The electronegativity, epsilon, number of valence electrons on the element NV, etc., have been used for this thing. Okay, and you can have a you can find a discussion of these things in this particular paper. Okay, but so far these features have not brought in any information about the structure of the molecule. So next, we have to go to features that encode structures also. So we will start that discussion in the next lecture. So that is all for today. And this will get a bit mathematical, bit formal. But then the good point is that you really do not have to code these things. You have ready-made libraries available, but you must understand what you are doing, because otherwise, you know, you are you're just walking in the dark, so that is not a good idea. Okay, so I think that brings us to the end of the discussion today. If you have any questions, again, please write in. I'll wait for a minute or two. And yeah. Yeah, Shubhankar, do you have any announcements to make?
Yeah, sorry, there was a mic issue. Okay. Yeah. Okay. Yeah. For those who are submitting projects, just a quick thing. Person, I will share the screen.
Yeah, just a minute.
Sure.
Stop sharing. Go ahead.
Yeah, I hope this is visible. So this is course website. We have shared it over email. Under the course website, we have sent emails to all of those who are taking credits as well as non-credit course. Those who are taking credit for this course, you definitely have to submit the projects and give exams at the end. Okay, not definitely, but to score points, of course, you have. So if you go just below and down, if you see, there will be like a grading scheme is there, main components and exam is there. And then if you see submission of project, something called open review. So I told you maybe we can spend some time in making you actual machine learning scientists. So majority of all the conferences that happen or journal submissions that happen through machine learning are generally done through open review. So if you click on this particular link, it should take you to the open review page where I have basically created a venue where you can post your projects. Yes. So if you come to this particular link, which say machine learning for material sciences, what you have to do is first you have to, of course, once you, for example, here you should say NISER 2025 MLMS submission. You just click on this. For me, it opens directly because I am logged in. For you, you have to create a profile and then login. This does not depend on Google or anything else. So all of you are like, please use whatever email address you have and create a profile. And if you plan to do long-term research in machine learning, make sure you create the profile in not a funny way. This is very serious. No? Everybody can look at this. So the open review in the part here means open. That means here all the review comments that come to your paper. Let's say you submit a paper, they are open to public in the later. So even if your paper is accepted, all the people later, like after the paper is accepted, they can look at the paper as well as the review comments, what the other people gave the reviews and the rebuttals that you submitted. So everything remains open for as long as open review lasts. So this is how machine learning community does in recent years paper publication. So here, if you come machine learning material sciences, here if you are at like a team, the title, the author. Once you have registered, if you search for somebody, I will just search for, let's say, like she's my student, so I found out like Rucha, then I can just add her. So she becomes my like co-author in this. So similarly, when you have two teams, you can just search for somebody. Once he or she has registered, then you can add them as authors. You can then change the order of author, but here both are equal contributors. Alphabetical is fine. You'll add some keywords, you add some TLDR, and you write an abstract, and then you can submit a PDF. Here, if you don't have a PDF, we have no issues, but in the abstract itself, we expect that you submit that particular YouTube link of 5 minutes explaining stuff. Yes, and your signature is just yourself, and then submit. And then once you submit, comes up as a submission into machine learning for material sciences. And what I will do next is I will assign other authors as reviewers for this. So they can come and look at your submissions and they can post comments. Okay? But that is for later. But given Monday is a deadline, just repeating. So you come to the course website, submission of a project through open review. There is a link. If you click on the link, this will open. Here, if you have logged in, you can just click on NISA 25 MLS submission. Anything that is star has to be submitted. It's a required form. You add your authors, like your co-author, your partner, keywords, TLDR, abstract, and then submit. So, and the deadline is Monday. The website will not accept any more submissions after Monday. Yeah. And any changes, if I have to require, I have to connect the open review team, which sits in USA. Day and night matter thing, so it will delay. So I hope you submit it within a deadline. That's all from my end for submission. You will enjoy the submission process and you'll fine. That's all from my end.
Yeah, okay. So I think I'm also done for the day. We'll have some other discussions on features next time. And I think they will be, by that time, they will be in a good shape to sort of,
Submit.
yeah, what to do with machine learning for materials.
Yes, and like initial idea, we expect that you at least have an idea in your mind. This will keep on changing, and that's
Yes.
like okay. I think Professor Singh will also agree. This will keep on changing as you learn more things and what to do, what not to do. But this should all reflect in your project documents. As in next time in YouTube video, when you promise in like midterm, okay, this is what we thought, and this got changed because of this, that got changed because of this, and this is the new milestone we're planning. And that's perfectly fine. This is what we expect you to go through the materials and the algorithms and the new data sets. And if something new idea that comes up to your mind and you create something really new, all are appreciated. We welcome. Fine. That's all for today.
Okay.
Yeah. Bye. Bye all.
Bye.